This video is a step-by-step solution for the example entitled Evaluating Expansion Work. In this example, you will learn about evaluating the expansion work of a gas in a piston cylinder assembly between set initial and final state on the three different processes. Let's look at the problem statement as given to us. A gas in a piston cylinder assembly undergoes an expansion process for which the relationship between pressure and volume is given by PV to the n is equal to constant. The initial pressure is 3 bar, the initial volume is 0.1 cubic meter, and the final volume is 0.2 cubic meter. Determine the work for the process in kilojoule. For scenario A, n is equal to 1.5, scenario B, n is equal to 1, and scenario C, n is equal to 0. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. A gas in a piston cylinder assembly undergoes an expansion process for which the relationship between pressure and volume is given by PV to the n is equal to a constant. The initial pressure is 3 bar, the initial volume is 0.1 cubic meter, and the final volume is 0.2 cubic meter. Determine the work for the process in kilojoules for A, n is equal to 1.5, B, n is equal to 1, and finally C, n is equal to 0. Let's start to develop the solution. The first thing we do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in our critical read of the problem statement in a bulleted list format. A gas in a piston cylinder assembly undergoes an expansion for which PV to the n is equal to a constant. The next thing is to summarize what we have to find. This is again the same information we highlighted in green in our critical read of the problem statement, presented again in a bulleted list format. For each of the three values of n provided, namely 1.5, 1, and 0, evaluate the work. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few key pieces of information which will help guide our solution. The first thing to note is there is no mass entering or leaving the piston cylinder. This immediately suggests that a closed system approach is appropriate. Having recognized this important fact, let's select a system boundary. Remember that a closed system does not allow any mass in or out through its boundary. Here it is selected to enclose the gas and follow the physical boundary of the piston cylinder assembly as delineated on the schematic with the red dashed line. It ties in the information provided to the information requested, namely the initial pressure and volume given, the final volume given, and the relationship between the pressure and the volume for the gas expansion process. The next step is to develop an appropriate diagram to represent the process. In this case, the PV diagram as shown here for three values of n. Case A, n is equal to 1.5. Case B, n is equal to 1. And case C, n is equal to 0, which correspond to a constant pressure case, also known as an isobaric process. Note that the area under the curve in the PV diagram can be interpreted as the value of the work, here shown as a shaded area for case A. The next step is to develop an engineering model. In other words, listing a set of simplifying assumptions which will allow us to perform the analysis of the problem. The gas is a closed system. The moving boundary is the only work mode, and the expansion process is a polytropic process. Having completed all the required initial steps, let's develop the analysis. The required values for the work are obtained by integration of the equation for expansion and compression work using the pressure-volume relationship. For scenario A, n is equal to 1.5, let's introduce the relationship P is equal to constant divided by V to the n into the equation for the compression and expansion work and evaluating the integration as follows. W is equal to integral from 1 to 2 of P dV, or integral from V1 to V2 of the constant divided by V to the n dV. Performing the integration between the limits for the volume at state 1 and 2 yields the following expression. Note that this expression, to be valid, the denominator n-1 cannot be singular. For this case A, with the value n is equal to 1.5, the denominator is equal to minus 0.5, which doesn't lead to any problem. In order to evaluate this expression for the work, the only thing that remains to be done is to evaluate the value of the constant for the polytropic process, which is what we'll do next. The constant in the expression can be evaluated at either of the n states. The constant is equal to P1 V1 to the n or P2 V2 to the n. Substituting the expression for the constant into the expression we developed for the work yields the expression shown below, which simplifies to W is equal to P2 V2 minus P1 V1 divided by 1 minus n. As mentioned earlier, this expression is valid for all values of n except for n is equal to 1. The case of n is equal to 1 will be discussed later for the solution of part B. To evaluate the work W, the pressure at state 2 is required. This can be obtained by using the pressure-volume relationship for the polytropic process between state 1 and 2. P1 V1 to the n is equal to P2 V2 to the n. Rearranging the term and substituting the given numerical value for P1, V1, and V2 is shown below, which gives a value of P2 is equal to 1.06 bar. With the values of the pressure and volume now known at both states, we can numerically evaluate the expansion work as shown below. In this expression above, note the required unit conversions needed to convert bars into pascals and joules into kilojoules. This yields a value of W is equal to plus 17.6 kilojoules, which is the answer we were seeking for scenario A for n is equal to 1.5. For scenario B, for n is equal to 1, the pressure-volume relationship is PV is equal to a constant, or P is equal to a constant divided by V. The work is then given by the following expression. W is equal to a constant times the integral from V1 to V2 of dV over V. By integration, we obtain the following. W is equal to a constant times the log of V2 over V1. Substituting the value of the constant evaluated at state 1 yields the following expression for the work. W is equal to P1 V1 log of V2 over V1. By substituting the given value for the pressure and the volume, we can now numerically evaluate the expansion work as shown below. As mentioned in part A, we need to be careful with the required unit conversion needed to convert bars into Pascal and joules into kilojoules. This yields a value of W is equal to plus 20.79 kilojoules. This is the answer we were seeking for scenario B for n is equal to 1. For scenario C for n is equal to 0, the pressure-volume relation reduces to P is equal to a constant, and the integral becomes W is equal to P times V2 minus V1, which is a special case of the expression found in part A. Substituting the numerical values and converting units as was done before yields the following value. W is equal to plus 30 kilojoules, which is the answer we were seeking for scenario C for n is equal to 0. In closing, I would like to make a few comments. In each of the cases, The work for the process can be interpreted as the area under the curve representing the process on the PV diagram. Note that the relative areas shown graphically are in agreement with the relative magnitude of the numerical results we obtained. The assumption of a polytropic process is significant. If the given pressure-volume relationship were obtained as a fit of experimental pressure-volume data, the value of integral of PdV would provide a plausible estimate of the work only if the measured pressure was essentially equal to that exerted on the piston face. Observe the use of unit conversion factors in Part A and Part B. This is one of the most common numerical mistakes. The units of pressure, volume, and work must be made compatible. In each of the cases considered, it was not necessary to identify the gas or the liquid contained within the piston cylinder assembly. The calculated value for W was determined by the process path and the end state. However, if it was desired to evaluate a property such as temperature, both the nature and the amount of the substance must be provided because appropriate relations among the properties of this particular substance would then be required. In summary, in this example, we have learned about evaluating the expansion work of a gas in a piston cylinder assembly between set initial and final state while undergoing a polytropic process. We evaluated this work under 3 different scenarios characterized by 3 values of the exponent n of the polytropic process. This concludes the step-by-step solution of the example entitled Evaluating Expansion Work.